Paper of the day is Reducing the Dimensionality of Data with Neural Networks. High-dimensional data can be converted to low-dimensional codes by training a multi-layer neural network with a small central layer to reconstruct high-dimensional input vectors. Gradient descent can be used for fine-tuning the weights in such an autoencoder networks, but this works well only if the initial weights are close to a good solution. Paper describes an effective way of initializing the weights that allows deep autoencoders networks to learn low-dimensional codes that work much better than principal component analysis as a tool to reduce the dimensionality of data. Dimensionality reduction facilitates the classification, visualization, communication, and storage of high-dimensional data. A simple and widely used method is principal component analysis, which finds the directions of greatest variations in the dataset and represents each data point by its coordinates along with each of these directions. They describe a nonlinear generalization of PCA that uses an adaptive multi-layer encoder network to transform the high-dimensional data into a low-dimensional code and a similar decoder network to recover the data from the code. So in this diagram, as we can see, pre-training consists of learning a stack of restricted Boltzmann machines, each having only one layer of feature detectors. The learned feature activation of one RBM are used as a data for training the next RBM in the stack. After the pre-training, the RBMs are unrolled to create a deep autoencoder, which is then fine-tuned using the backpropagation of error derivatives. So as you can see, we have the pre-training, unrolling, and then fine-tuning. Take a minute to appreciate this image. It has been obvious since 1980s that backpropagation through deep autoencoders would be very effective for nonlinear dimensionality reduction, provided that computers were fast enough, datasets were big enough, and the initial weights were close enough to a good solution. All three conditions are now satisfied. Unlike non-parametric methods, autoencoders give mappings in both directions between the data and code spaces, and they can be applied to a very large datasets because both the pre-training and the fine-tuning scale linearly in time and space with the number of training cases.